This is the Amp Hour Podcast, released August 2nd, 2020. Episode 503. Fabless Chip Design with Mohamed Kassem. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
I'm Mohamed Kassem, co-founder and CTO of Fabless.
Welcome. How are you doing?
I'm very good, thank you. How are you?
I'm great. This is so fortuitous timing. We had planned to meet, but then some of our scheduling stuff it didn't. Some of my schedule stuff didn't work out with another guest, and you were able to join me here today. And I'm really glad you are, because the timing couldn't be better, given the fact of the coincidence of Tim being on the show last guest episode, and obviously the Google PDK, Open PDK stuff with Skywater and eFabless doing a lot of the. You guys are doing the handling of the 40 designs as well, right?
Yeah, that's actually a part of the picture. So eFabless started by actually releasing the open lane. That's an environment that people can use to build these chips for the slots that are going to be on the shuttle, both sides, front end and back end. And we're actually in the process of publishing how this is going to work. And people are asking how and where do I go to submit my shuttle, and they need more information. So we're working very hard to do that quickly.
Great.
Because the community is actually very engaged. So it's a positive thing to get here.
Yeah, that's great. That's great. So let's take a step back for people who didn't maybe listen to the last guest episode. Could you give us a quick rundown on what some of the news is, and what's been happening in this world, and then after that we can go talk about how we got to this point.
In the worlds of semiconductor in general?
More about the Open PDK and the Skywater stuff and Google and all that.
So just as in the general in the semiconductor industry, it had historically closed in terms of the sharing intellectual property and knowledge. They're contained in pockets within companies or subgroups or universities. And in order for someone to be able to, even a small company, to be able to make their own design or just choice of design, if that's a choice to them, they need access to the foundry. They need access to an IP, like functional blocks that they can put on the chip, interfaces, etc. And they need software, AIDA software. You need maybe complementary knowledge that they don't have. So, and testing capabilities, etc. So if you put all that together in a one big AND gate, that's what I call it, get zero in the end. If any one of these don't exist, you can't make a chip. So it is, as we go forward, if you notice in the news in general, the companies, semiconductor companies have been buying each other, and the number of semiconductor companies is going down. And that means there's less flexibility for the agile people who are very knowledgeable and willing to take risks.
Yeah. So if you wanted to differentiate yourself in the market, it would be really tough, I think. As we talked about this last week about analog buying Maxim, and then you talk about how do you differentiate yourself from someone another small company that's using the exact same chipset. So it's you have software, but if you want to differentiate yourself at all on the hardware side, it becomes very, very difficult, it seems like.
Yeah, and in order to be able to, just historically, just the idea of having a custom chip, it rings a bell right away of $500,000 to $1 million of a start. So people are just like, I'm not going to think about it, because that's the way it is. Mm-hmm. And not knowing that originally, when I used to work, with Texas Instruments and the wireless engineering group, and the volumes of the product are, you aim for 100 million units. So which is the investment would be, no matter what, it's going to be too small. So you do a custom chip for that. Now, it became this way, and the AND gate became an obstacle for small innovation, for small ideas to come to the, or new ideas to come to the, even try to prototype versus market. There were open source softwares and EDA that existed around this ecosystem, but they're different units or separate engines. They're not a flow. So you would have or at a simulator, the synthesizer, the layout checker. Every one of them is doing something and it's working on their own world.
Hmm.
So there was a need for something to happen to aggregate or to glue all that together into something that other people can use in a useful way to actually get some silicon out of it. Just as a background, and I'm leading to the Google part here, is as a background. So when eFabless started, we the approach is very simple. We wanted to have in the browser give anyone the ability to design anything they want on a custom chip and put it in a marketplace that a customer or a collaborator can work with them on it. And when you think about just what I just said, it implies two things. It implies that the end gate, all of it would exist in the cloud in a portal where someone can I can communicate with someone for knowledge. I can use the EDA software. I can access to the foundry. All of that is in one place, one cockpit. That, if you think about how to do that with a commercial or a traditional ecosystem, you're going to be very quickly in the impossible space: foundry,
That's
IP,
right.
and EDA.
Yeah. Right. I'd say even just the EDA, it's like, yeah, I guess we'll just, our startup is we basically bought 100 seats of Mentor graphics and we just put it accessible online. And yeah, I mean, that's how you do a startup, right? You light money on fire and
Yeah, yeah. So luckily, I had some understanding of some of the goals of the EDA companies back then when I was around 2012, and I approached them to entice them to have a change in the business model justifiably. They, which it's very well understood, it's that their economic model is not suitable for that. So I immediately started doing looking or on a mission for open source engines that actually did something that's successful. And
yeah,
I literally traveled the world and I put in, and got the right people, and had the honor of getting to the privilege of knowing them in more details and visiting them in their homes. Anyway, we got
yeah,
all that
yeah,
and we started putting the first stack. It was an open source environment and it didn't have an open source process.
yeah. So yeah, and it sounds like, I mean, so you knew all this, you knew all the steps anyways because of your past experience, and I'd love to hear about that at some point. But you basically had to build, like you're saying, you had to build all these more open source or really more low cost. It seems like is the real key to make it accessible. And so you had to build up each tool and each layer, not build it yourself, but build it up as a ecosystem. And then once you did that, and present day, it's like there's enough tooling out there to actually make it accessible. What about the open PDK? The last layer actually enables someone to go and make their own chips now. So like, why was that the gating moment, or was it?
Well, it was because if you think about it, the PDK is if you think about it as an intellectual property of the foundry. So if the foundry is protecting it and requires you to protect it, then you have to. So the middle ground was we put the open source solution on the cloud and we put the foundry PDK on the cloud as well, but obfuscated. So
Uh,
so people can use it from the portal, but they cannot download it because download implies full exposure. So we worked out with two foundries at least to have that agreement with them in such a way that you can go to the website right now, log in, you can use 130 nanometer on Global Foundries or 180 nanometer on XFAB, and very soon it's going to be 130 nanometer from Skywater. The difference is now when the PDK is open, it's exactly what you saw here. I can go to GitHub, get the PDK built, and I can go to get Open Lane built. And then on my computer, I have the ability to run both and do a lot of iterations. By the way, on both sides, the software and the hardware. So as the minute you publish these things out, people started testing and trying their own things that you wanted to try, and then someone would add a feature and say, okay, it would be good to add this to the software to Open Lane, okay, and
yeah,
or find an issue, missing information in the PDK. So there was a lot of open collaboration. So when you think about the two worlds, I have to collaborate within the building and invite people to the building carefully, versus I'm collaborating in a distributed world where I am sitting on Slack talking to people that are in different time zones. I have a goal is to get this environment to produce chips to put
Yeah.
them on the shuttle in November.
Yeah. So it seems like it's reducing friction at every step, including at the developer step. The thing that I guess I wanted to call out though is so you mentioned a lot of this, you wanted it to be in the browser. The fact that it is downloadable though, what is the split of like, is it possible to do everything in the browser, or is there a realistic, if you really want to customize things, it has to be on your local computer?
So the browser versus not is the browser is nothing more than a delivery window. At the end of the day, I call it a remote display. So it's whether it's in the browser or some other X client that you use locally.
Hmm.
But so the challenges typically with that is internet latency or data center to, so the latency to
Sure.
the right place. In the US in general, you wouldn't see that problem. You start seeing it, for example, in India. So we end up deploying or looking at other data centers for the cloud provider that we're using. That said, because of that latency, you put restrictions on the size of the design that you're going to look at because it's going to refresh in a long time. Or so
Mm.
these are things that are challenges. However, they haven't stopped people from continuing. We have people, at least a lot of people from India, a lot of people from the Middle East, Europe, and of course here in the US, but they don't have that latency issue. They don't see it, so it's actually very snappy when you try it from a good internet, low internet latency. It's not about the
Hmm.
bandwidth; it's more it's at some point in the latency. It makes a difference. Now that is not the issue for the open source side.
Yeah, it seems like a nice to have versus like a must have kind of thing.
Yeah, the only reason we had it in the cloud, it's simple, is the Foundry and other IP providers, other blocks, were trusted. They put them available in an obfuscated way so the community can, on the other side, use them without seeing what's in them. So the
Yeah.
eFabless
Like
was,
black
in this
black box
case,
kind of idea, like just
exactly
inputs and outputs, transfer functions, all that kind of thing.
correct. And eFabless was the kind of a straddling the two medium, one leg in the, and it's still we do. So now we have companies that don't want to open their IP, but however, the open source community can upload their design and hook up to that IP. And so we're straddle that medium. Now, when you download it, you can do everything off the platform. And then when you're done with the design, we have a process that will absorb it from your repository and then check it and, against a set of checks so that it becomes manufacturable.
Yeah, that's great. That's great. Before we dive into the flow, because it does sound like it'd be really interesting to kind of walk through the flow here. I mean, we talked about that a little bit with Tim, but I think that it would be a better to kind of do each step here with you. How did we get to this point? I mean, so you mentioned 2012 is when you were starting this, but why this? Like, what made you decide to go in this direction in the first place? As someone who's had a lot of experience in the industry.
So I always, this is personal. I always enjoyed working on new things. Even when in my previous life, before I started a company, I was working in the smartphone chip development area, which is back when, if you, from 2000, year 2000, this was the height of the smartphone, and it was very, very good opportunity to learn, and it's like a boot camp. So I learned a couple of things. Is that you can design, you may not depend on the tools so much, and you still can design, because we had these issues inside the company and we got around them. So I learned a lot of the how do you do it with a low confidence, or if you have a low confidence in the tools, for example, or the models. Or so one of the things that I looked at and actually saw it very obvious in front of me is that inside the companies that develop analog chips, only like smaller, like you can actually have two engineers inside the company responsible for a complete product, and the
Wow.
rest of the resources are coming from the company, whether it's the infrastructure, tools, access to the fabs, etc., testing, all that is infrastructure. So it hit me. That's just the thought, and I'm not sure. I'm sure it's not necessarily a unique thought. It may have come to many other people. And by the way, this is actually a spectrum. The chip complexity is a spectrum. So there's the chips that we can actually one person is developing, and there's the chip that has 150 people on it. Okay, so So I looked at the other spectrum, the right side of the spectrum, and then I found, is there a possibility to produce something or replicate a model that looks like the Apple App Store
Mm,
in a way where people can design at no cost or and get a development kit of some sort and then deliver in a marketplace. So
mm,
that's the general concept. When I thought about it, it started to evolve very quickly, and I decided to take a risk at it and just I wanted to actually do it cleanly. So I I didn't even have the Ford formulation. So and I left TI to try to solve the problems one on the AND gate one by one, including the
mm.
foundry.
Yeah. Yeah, that's a lot of steps to to get there for sure. On the App Store side of things, I mean, did had you been talking to engineers who wanted this sort of thing, or had you seen it, or is it more of a kind of a feeling that this technology's time had come and you're just kind of ready? You feel like if you build it, they will come.
Well, it was not exactly it was an intersection from a few points. So I was looking at places in the software world, like a company called Topcoder. It's a pioneer in community-based software development, where you can throw a problem. It could be a data set problem, data analysis problem, all the way to building a small app, and then the community will actually come in and contribute and develop that for companies, for like IBM, for example. So there are precedents in that model where the community can in the software world. And then I noticed also I had, when you say the feeling, the data points around the open source world where people are accessing the software, but it's always stopping short of a complete design that can go to manufacturing.
Got it. Yeah.
And I thought this is basically the piece that I thought it's going to be. I'll build a you'll get there is when we put out the solution, people will come because it's a valuable solution and it's not offered before. And
Yeah.
and that was actually it was a bit of gut feeling, and the gut feeling is developed usually from your experience around talking to people and seeing
Yeah.
how it
Exactly.
works. But there was no definitive like, hey,
Yeah. No
uh,
one walked up to you and said, "Hey, Mohammed, could you please design this this market ecosystem for me? That would be I really need it. If you could just get it to me
yeah.
whenever you get a chance, that'd be great."
And I have to say, the learning. I mean, you get to learn by fire and everywhere, and you try a lot of things, and you take feedback from people. And so I call so as we evolved since then, is a lot of it is by learning and working with a lot of people.
Yeah, I'm sure there's been a ton of learning. I mean, so one thing that's interesting to me, and I think I might ask Tim this as well, but like, so like from my personal experience, I don't see myself making a chip anytime soon, right? But that's also because I'm small potatoes. I'm not working on, high volume products. What is your take on when it makes sense to go and push some custom silicon? Like what is the volumes that it takes to do this? Because maybe it's just that I'm not even near those volumes and but some people are often working in that world.
So the volume question mark came from just a simple economic formula, which is if you're gonna spend the money and the resources to build a chip with engineering, you need to sell enough to justify that money. That's simple. And
Got it. Yeah.
if you're selling one unit, let's say imagine you're selling one unit, then the entire engineering project budget would have to be converted into the baseline for the chip for one unit. So imagine that.
Right, right. Yeah, the first chip cost 10 million, the second chip cost 10 million, and
yeah.
$1 or whatever.
So now that said, the world is now, when you talk about chip and ASICs, very quickly they jump into the advanced technologies, 40 nanometer, 28, 22, it's 14, 12. And when you hear these numbers, the upfront investment, yes, tens of millions. And in this case, it doesn't make sense. You have to have the volume. You have to. And the
Yeah,
smartphones,
right.
when we worked on them, you have to, because the smartphones were exploded. Have more than half the planet have smartphones, have phones. We wanted to convert the formula into change that into remove the the volume question mark. And how is that? If you reduce the barrier for someone to get the prototype, there are a couple of things. They can actually prove something and they can get investment maybe. The number one question is people will ask, do I need an ASIC? Well, the trade-offs between an ASIC versus two-chip solution or some other multi-chip solution is something that knowledge is residing typically on the IC side. And that means that a system developer, they wouldn't necessarily contemplate or figure out, just to quickly say, okay, I can do this on a chip. Or maybe they would, but immediately the economic part kicks in and it says, like,
Yeah,
well, it's going to
right.
be too much.
Right. Yeah, so it's like having a tool in your toolbox, but that tool, the nail costs $1 million, and you're like, well, I'm not using that nail because I don't think it makes sense.
Exactly. So if you change the economics and say, like, for example, in the high volume world, you have to make the device area very small so that you can maximize the number of devices per wafer. And in this world, I say, well, is area so important if it's a low volume? And if it's not, then I can actually relax some other component and change the formula here. At least change the NRE, the amount
Right.
of money being spent upfront. So if you reduce that amount of money by providing tools and by providing the access to the foundry, then that budget that I said it would be divided on volume would be divided on a smaller amount, much smaller amount. Like you're talking about 10x.
Yeah, that's great. And so okay, so then let's play with it though. Like so you've now gotten the cost down. You've got the chipset is available, it's accessible, it's easy to use. All things that it seems like we're driving towards. But then the reason to do it is what? Security or power or like what are the reasons to do it after that then? Or uniqueness?
So there are multiple reasons. You mentioned at least two of them. In cases where you'll be able to use lower voltage because of the chip, or you integrate two chips on the same die, you change how the IOs and all the power requirements work. So the power is something, but it's not necessarily a given. So it always has to be analyzed, and because there are chips that are consuming more than systems. The other side is security. Security here is kind of interesting because I call it protecting your own IP. So if you have a specific algorithm, we working with a company that has their own specific algorithm to manipulate data coming from the sensors, and this is something that they use it for their product. So they have a full product and they do the chip, but they buy the chip. So they wanted to replace it for supply chain reliability because they only had a sole source and they didn't want to be dependent on it. So they wanted to initiate another design to create a mitigation of the supply chain.
If anyone's gonna mess up my supply chain, it's gonna be me, darn it.
Well, yeah, and basically they're working with another company, and the company's great and everything, but he basically said if that disappears, and he looked at the investment, he came to us and looked at how much money in there, and then it made it easy. Coming back to the question was, so the power, the security, or protecting IP, form factor, and just pure volume like space is actually miniaturization is important. Is when you need that when the product is at the level like we were at the back in the smartphone days. You just say you need the chip to be no higher than that, the height, not just the area.
Right. Yeah, you can't make some 4 millimeter tall SIP or something like that.
Yeah, exactly. And so and another example is just an earpiece. So now how much do you want to put in if you couldn't actually put this electronics inside a chip that gets in there? So the miniaturization is an important aspect as well.
Okay. Yeah.
The last thing actually is obsolescence mitigation, which is
Mm.
some people would have a complete board that is ancient, the parts don't exist, and you could have the option of designing. Somebody would design it again. It's either by replacing it with some multi-chip solution again, Or if you know that the trade-off of with the ASIC will make it easy, then you can make that decision. And that's actually one of the
Yeah.
things we're doing, trying eFabless, is to make that judgment easier. So we give cost numbers and information as you are choosing what to be on the chip, what to exist on the chip.
Yeah. Yeah, I can imagine even with the upfront cost, there still is going to be upfront costs, which we'll get to, but even that, you balance that against a last time buy of, buying 10 years worth of parts. Well, it might be worth it to go and spend the NRE up front and make something that you can make for as long. I mean, then you have the design files effectively, so you can make it as long as you find a fab that will push out the chip and validate it for you.
Yeah, and I have to say that if you really want to speak of it in realistic numbers, if you're designing your own chip, like you're actually bringing your own time and effort to make your own chip, the number goes down below. I mean, it could be well below $10,000. Okay, if you want to, in some
Oh
process
wow.
technologies.
Okay.
So it's a credit card question mark. Okay, and people will hear that and say, "Well, what kind of chip is it? Does it have SerDes? Does it have the USB? Does it have?"
Yeah,
Well,
right.
no, it doesn't. Okay,
No, it's got what you need, but not much else.
exactly. And
Yeah.
so you can go that. An example with the Google shuttles. What's happening now is that people have the tools, but that number that I was talking about, the 10,000, is gone. So because Google said that we're going to sponsor these shuttles so that people can uh, uh, use it, prototype. So that is one component. The other component, which is interesting, that's kind of hidden, is that if you have an idea and you believe it's going to be super useful and a lot of people are going to use it, if you go pitch, you don't have the money. Okay, so you want to get investors, for example. You go pitch it. The slideware plus your experience and maybe the team will be the only indicators whether that is executable or not, can be done or not. Of course, can be done meaning that you deliver on the chip, assuming that there's something that's hot in the market that people need.
Yeah. Right.
How many people get filtered at that stage? I have an idea and I will do make it, and then no, you won't make it. We know you won't make it. I mean, that's how many people have told me that
Right.
we won't make it, and we won't basically be able to run open source tools or any of that. So by having an upfront cost, for example, you come in on our platform, on the platform, or actually open source on the open source world, you can develop all the way to finished chip. That actually is a lower risk stage. So if I want to go to an investor, I can actually say that I have this. I've developed it. I have a pre-silicon. I've already done it because everything was open source. I cut a lot of the risk for you.
Yeah. Right. It's like having the access to like an AWS server now versus like how it used to be. Would had to build up a small data center and prove out your idea and have the stack and all. So you're saying that now you can just go and rent an AWS server effectively and do that for a chip. That kind of idea.
Yeah, and then in that case, that $10,000 I'm talking about, even if it's 20, then it could be the customer or the investors. It's like, oh, I'm willing to do that so I can see whether this is going to be, realistic or not. But
Right.
I'm working
Yeah.
from a real design, not from a theoretical design. So
Right.
that's an important to move the money from the idea to the prototype.
Yeah, that's a good idea. And yeah, and again, you don't have to invest in even the tool chain and you know beg, buy, and borrow
Uh,
the.
your own time.
Yeah, it's just it's your time. It's going back to a garage startup where you're actually you don't have to fund the mentor license or the to be working in that garage.
Yeah, and this is actually we have good examples. Like we have the Raven microcontroller that we developed earlier. That is a great example for collaboration. So the CPU developer is somebody from Clear Wolf from Austria, and they had the CPU. They don't have access to the foundry or the IC tools. We have access to the foundry with analog IP. We have system integrator. So it was built in a collaborative way over the cloud, and and we ran it and we made it to silicon and we published it, and people now have their own work, the open source work, first time on a real silicon versus an FPGA. Now, whether or not that's cool or why would you do it, well, it is actually, it said this, it actually opened the door to encourage people to say it's actually possible. I mean, when the team did a microcontroller based on a RISC-V CPU with 100% open source tool set, it invited, there is something there.
Right.
How is the performance comparable? Maybe not. Okay, but is it enough? So that microcontroller runs on 100 megahertz. Okay, and is it enough for some applications? Yes. So, and this is where that was the Google discussion about getting the working with the foundry on the open source process.
Yeah, so I mean, that's a great transition, I guess, into some of the stuff that's on your site, and then maybe we could talk about the flow as people are using it and deciding to go towards, making a chip. So you mentioned the Raven microcontroller that Claire designed. What is it that people are going to do each step to get towards making their own chip? So if they're in the garage, they're like, all right, I'm ready to prove out this $10,000 design to this investor I have. What are all the things they need to do to get to the actual silicon in their hand?
So if you think about it, if you think about the AND gate, when you work on something like on a fabless platform, everything in the AND gate is available. Now, the most important part is knowing is the knowledge. So if you're doing it yourself and you have the knowledge, or you have someone complements you in that knowledge, you just go to the website, and not only will you find the tools to start from, you'll find functional proven silicon IP. Again, you ask me what they are. Are they USB and SerDes? I'm going to say no. But they're actually proven, coming from the foundry. And not only that, Raven is, as a chip, integrated and tested together, is available for you to clone it and make modifications to it instead of building it from scratch.
Yeah. Yeah, that's one thing I had asked Tim about as well, as like a starting point to, because that is so often, like that's how I learn a lot of things is, I start from a development board effectively, and if there's nothing like that in the silicon world, then what?
Exactly. So Raven, so we have a board for it. That board, people who partnered with us have used it, and as a matter of fact, there was a customer that took it, and the second a couple of days after we published the Raven, they were interested in it. So the board existed. So not only can you touch it, you can experience it, you can understand the peripherals and know what it is, but you can actually clone it with even verification benches and things that help you attach other peripherals and things you put in. So that reduces the time first, the effort. So if I'm an analog designer and I know a certain focus and I want to develop a state of the art or some new architecture of an ADC, for example, I can use the rest of the chip just by unplugging that and putting mine. So, and there's no cost for the chip itself as an open source design. It's up to public out there.
Mm-hmm. Yep, that's great. Okay, so they start with the Raven, and then basically they're downloading the Verilog effectively, and then stepping through with OpenLane, and like what are those steps?
Specifically, Raven, it was done pre-Open Lane World. It was done a couple of years ago, and it was done with Keyflow. It was managed by it's one of the star flows that coordinated and maintained by Tim Edwards of OpenCircuitDesign.com, and so that's what we used. And then Raven had an interesting missing part, is that the IP inside it, not all of it are open source. So although you're going to find RTL, so actually when you clone it, you'll be able to get the RTL of the top level and RTL models for anything inside the chip. You can simulate it, you can add your own, as long as you use the Lego blocks that exist, proven, that are on the platform that are provided, for example, by XFAB. Not and Raven, so there is a constraint in Raven because the process and the IP were not open source. So in Raven, when you clone it, you're not going to download it. You can actually just clone it on the platform, put it in your own workspace, and do whatever you want with it. And some people will consider that a constraint. Some people will say, I didn't even have that before. So another example I'll tell you, ARM today we have an agreement with ARM. For example, you can actually get to our platform, use the one of their cores like the M0 without talking to ARM. You just right there within minutes, you can actually be able to use it and put it in a system and simulate it and compile it, etc., without actually talking to me or
Got it.
ARM or anybody.
So you're saying that in order to use this kind of more closed off, if there's something that's not completely open, as long as it stays on the site because it's behind some levels of obfuscation, it's no problem. Like having you don't have the RTL of the ARM zero M0, you don't have the
Yeah,
the
we do.
RTL of
Yeah,
everything.
we do have it in our like Fabless and Backend now, but you
Sure, yeah,
can.
yeah. I mean, sorry, I was saying you as the user.
And
You know,
that type of story and setup made it comfortable for people to say, I can give that, put it here so that other people can use it, because eventually it's going to sell more if people use it more. Or so, but the risk is less because they're not downloading the actual IP. That's if the supplier or provider of the IP is actually closing it. Now, in the new world, so well, actually, before we go to the new world, you clone it in your system, you simulate it, you verify it, everything is online, and then you request to be put it on shuttle, and then and this pay there's a payment there, and then you get back parts.
yeah, that's great.
So you can go clone Raven, modify it, add something to it. We did the same around ARM M0, so it's available there. Now in our new world with the OpenPDK, we have a family called Strive microcontrollers, and they are completely open. They will be on GitHub,
That's awesome.
and they're built using OpenLane.
Okay. And so Strive is like a core IP block that's like a RISC-V processor with everything around it. Is that the idea?
It's actually it's the first one is going to be the core RISC-V processor, the Pico RV32, because that's what
Hmm.
we used in Raven. So just we wanted to minimize new factors, so we jumped into that. It's
Okay.
going to have logic RAM and an interface, an SPI interface, and a clocking system. There's no analog whatsoever on it. And
Okay.
the logic RAM, because back then when we did it, there was no we didn't have the compiler ready, the RAM compiler. So we have another one, Strive 2, that exactly the same content, except that the RAM is not logic. It's a compiled RAM. Actually, you'll see it in the chip. That
Uh,
like a block versus
okay.
just the logic integration. And then we're adding other things.
Can you explain that a little bit more? Actually, I'm a little confused about what you mean there.
So the RAM, you can either implement it literally, like with a bunch of flip flops on your own, lower performance.
Oh, you're saying because it's SRAM versus DRAM?
Well, yeah, but you can use the elements of the library, the D flip flop, the flip flops themselves. You can use them to construct what looks like a RAM
Got it.
from the
Yep.
outside,
Yep. Yep. Okay.
and that means it's not regular. It's performance is lower, but it's a RAM. It's actually a legitimate RAM.
Yeah. Right. It's like it will store and
It will
randomly
store, and you
access.
can have access and all of that.
Yeah.
Now that is, if I show you the two chips, you're going to find that this one is bigger because you're implemented this way. The other
Hmm.
approach is that you specify the RAM size and parameters of what you want, and then you get a macro, you get a block, a rectangle. It says this is 8 kilobytes or 1 kilobyte of SRAM, and you
Hmm.
drop it outside the CPU, outside the chip, outside the main parts of the chip. And if you look at Raven right now, you'll see it. If you go to the marketplace and look at Raven, you find it's on the bottom right corner,
Hmm.
a separate
Okay.
block.
Okay. So it's something that yeah. So it kind of reminds me of like in like an FPGA, you can use the memory element of a LUT, or not even a LUT, but a logic cell, I guess, inside of an FPGA, logic cell unit, whatever there is. There's just a little bit of memory. There's a LUT in there. You can implement it like that, or then there's also block RAM that you can access, and it's just like each vendor kind of implements it different, but there's like this set amount of stuff inside the FPGA that you go and instantiate and say, no, this is a special type of memory here.
Yeah, yes, exactly. And the Strive, we actually have like now 6 versions of it, but because we're engineers and we want to take be logical and systematic. So the chips that the Strive family, which by the way I'll be talking about it on August 25th on the FOSSI Foundation
Mm-hmm.
dial-up program. I will be
Yep.
presenting the Strive family. And so it has, every chip has a different new thing that we did with open source. So the first one is done with OpenLane. The second one is done with OpenLane and OpenRAM. We used OpenRAM for, as the compiler for the RAM. So that's a new element. The third one, we didn't use the same library. We used the library developed by Oklahoma State University. Completely different library. It's the same function, so we'll be able
So
to.
just to prove that it can work on, it's not just this one dialed in thing. It's the process that can handle a lot of different types of inputs.
Yeah, and the good thing is that all of them are Strive, so they're expected to function the same.
And when you say Strive, you mean like that's just the brand of like the overall chip
The
design, or
family, the family, we call it Strive. So now the first one has the logic RAM, but it functions a certain way. The second one has a block RAM, but it also functions the same way. So I can actually have apples to apples comparison on the silicon when I put them together
got it? Yeah.
from outside,
Okay.
from the
Mm-hmm.
outside world.
Huh. That's great. That's great. So to go back to the flow. So okay. So now let's just say they're cloning the newer Strive thing. They download everything that's on there. It's got the open stuff. They put it through Yosis, and then OpenLane is to do the place and route. Is that right? Or the
So Open
routing.
Lane is actually the combination of a few things. Open Lane is intended to take you from RTL all the way to the GDS, all the way. So it includes Yosis, it
Mm-hmm.
includes OpenSTA for timing analysis, it includes something called Fault for DFT, and then it includes Open Road for floor planning, placement,
Mm.
and
Oh,
routing.
that's right. Yeah, sorry, I was confounding those two terms because they're so open lane is kind of the overarching flow for everything. Open road is the one that I think Tim mentioned as well. That was the one that the DARPA
Yes,
had worked on, right?
and the Open Road is just, we have to say it's a huge departure from the world of previous flows in the backend. Like you couldn't do beyond 100,000 gates to get them into GDS. We were able to get into a million with one shot. So, and this is actually, this flow is very capable of advanced nodes as well. So the UCSD team is working on a chip for 12 nanometer from Global Foundries.
Oh wow. Okay.
So it is actually a capable back end, and we intend to use it everywhere we can.
Yeah.
Um,
Can you explain what GDS is? Because we didn't really talk about that. I don't think we've talked about that on the show before.
so the a GDS is a format that is efficient in storing the data that you presented to the factory. So the closest example of that is simply the 3D models. So of when you go online and you have a 3D model, just a STL, for example. STL is a representation of uh, the, the 3D model that you're looking at for the printer to use to print.
Yeah. Right.
This is exactly similar. So it's a GDS is a graphic design system, and the it has the data that represents the 3D aspects of the chip, because every layer, the chip is a 3D-ish element. It has a, you build metals and you put it on top of layer by layer by layer. So it's actually kind of, you can make a very tiny 3D printer.
Right. 300 step 3D printer with yeah.
Yeah, and literally, yeah, and it has a
Very
combination of
expensive.
etching and additive and subtractive
Yep.
mechanisms, but it
Yep.
is essentially a 3D printed element that requires very high resolution to be able to print it. So that's the GDS. It's just a representation, and the data could get high, so very large in size. So there are multiple options and things to actually make it more efficient storage and reduce it.
Interesting. Yeah. So I guess when I think about it, so when I think about it, like in comparison to like a PCB, is it like a Gerber where it's like a flat format for each layer, and then you say, but then you also need levels in between to say, well, actually, even though here's the pattern of the oxide layer, that we need on level 30, then level 31 that you're doing as an additive layer, we need that to be at least 100 nanometers of oxide in order to get these certain properties.
So first of all, in the GDS, the standard practice is all of the, imagine the Gerber layers, the different Gerber files, they're all combined in one file to
Okay.
represent that's the number one. Now,
Okay.
if you look at the PCB, for example, things like their layer thickness, the electric constants, and things that are in between metals, and this is for a given substrate or a manufacturer, it could be fixed. So when you go to the foundry for the chip making, the oxide thickness is pretty much set into a few standardized, some for the transistors and some for just filling the what they call field oxide. But
Yeah.
once you provide the GDS and I do layer one, it is kind of known for that process what to do to basically deposit oxide, and or not oxide, they deposit chemicals to get the oxide, and then you add another layer by deposition, like the metal, you deposit it through the mask because it goes through the mask, and so it gets added layer by layer after. So the GDS is one bucket, and then you take it, they split it into several masks. Every mask has one layer, and then they use it to do like a silk screen printing on the layer below.
Yeah, positive or negative
Yeah, exactly.
as well, right? Do you need to take stuff away? Do you need to add stuff? That's like how you need to make sure that like you're not making a hole in something when in fact you actually wanted to fill everything around that one area or something like that.
Exactly. And when you said the oxide thickness, this is kind of becomes a parameter that is controlled in the process. So they want it to be to a big degree constant. Nothing at this level is absolutely equal. It's always a statistical process. But yeah, the oxide thickness is known for this technology, given technology.
Got it. Got it. Well, speaking of, so a lot of the stuff that you show on your site is 180 nanometer, but then you also referenced earlier the Global Foundries 130, and also I think you said an 80 nanometer. So, and then you said Skywater as well is 130. So, what is the current access that eFabless has, and then what just generally people might have in the future?
Right now, immediately, as it is today, anyone can access the XFAB 2 process technologies, 350 nanometer for high voltage and applications. It's a very good process for that purpose. And then 180 nanometer. Immediately you can go there. And not only will you access the process, you will find blocks that are data converters, comparators, PLL, things that you can actually use along with your own design. So that is XFAB side. Today, existing on the platform is Global Foundries 130 nanometer, 130G specifically, and you can design with it. And it's actually the front end. You can do the front end with it. The back end is going to be based on OpenLane, and it will be released in a couple weeks. So you can access the front end of the Global Foundries today, and then within a couple weeks, you'll be able to actually use the entire process.
Huh. And so front end versus back end, you're saying is that defining like the transistor level versus like the metallization layer?
Well, that's a one way of doing it. For process people, it is back end of line, front end of line. You're right. Now, the in the terms of the design, it's anything before synthesis. Once I start targeting the technology itself and mapping the design into specific technology, then becomes the back end starts. So anything
Okay.
RTL, Verilog, all of the system Verilog, anything before that is front end, and then synthesis is the bridge. And now you have the design is represented in components that are specific to this process. So now you take that and placement, floor planning, placement, router, etc., all the way to the end.
Okay. Okay. And then what about, so you mentioned, I mean, the Skywater PDK as well. So like, can you walk us through real quick, like what it takes to get a new fab onto your platform?
So there are two to three things, but there's the business aspect of it. So that's basically making the case for the foundry to believe that having this process on the platform that will potentially increase the number of designs and potentially increase the number of products that are being sold with that foundry. So that's a separate topic. Yeah, and unless you want to address it now, we can talk about it. And the second aspect is the technical part, which is the PDK is represented in a set of files that are compatible with the commercial EDA infrastructure or tools today. So generally, a foundry would, when you ask them for the PDK, they don't give you something that works out of the box with an open source tool.
Right.
They'll give
Yep.
you, yeah,
Yeah. Right, because they're basically. I'm sure that the large scale ADA companies are helping to develop this stuff because it's in their best interest to be completely integrated into a foundry's business.
correct. And actually, and this is a good model, and it has its customers and its market. So it's a, it works in that space.
Yeah, I mean, to make a crude comparison would be, like, I've talked to all these assembly houses. They're like, yeah, we use all these different formats, and we work really well with like Altium and Allegro and all these cadence things. It's like, well, thank God for spreadsheets and basically spreadsheets and Gerbers are the only reason that KiCad can operate in that space is because there is that standardized format. And it sounds like now the chip industry is kind of starting to move in that way as well because now there's going to be open PDK and it's going to get a little easier to integrate new things.
And partially that existed in, like in the layout, GDS is a standard. I can read GDS with any tool, any of the
Okay.
commercial
Yeah.
tools,
Yep.
Spice Netlist or timing models. Some of these things are, but however, there are not uncommon things that are enough to create the stickiness, meaning that when you use a certain flow, you stay with it. So now what we did to avoid to be completely clean, we went to the foundry and said, give us the information, the process information, not even the PDK, and we will take it and produce the same thing that is produced for the commercial system to work with the open source tools.
Mm. Yeah.
and and we take it from the foundry directly. They take the information, the process information. We don't even, because we don't want to even be in a way to do
Yeah.
any.
Because it's like interpretation almost of like data and how it all fits together. And PDK is like an abstraction of what's actually happening on the floor of the fab, right?
Exactly, in different views. Some of them are physical
Mm-hmm.
views, represent the layout, and some of them are simulation views, represent basically functional and parametric simulation.
Huh. So what is the work then that you have to do? So you take process information that's basically like what measurement of gate sizes and variance and statistical process control or what?
So to start with is, for example, the design rules. So the design rules typically they literally have a manual, a PDF manual, which is this is changed already because in the release with the Google, but that PDF manual has every rule and what is the metal spacing needs to be that much, metal spacing, this metal overlap, VSI. So all of that is written literally. We take these numbers and stick them into a rule deck that is readable by the layout tool. This is Magic,
Mm-hmm.
and that's a start. Now the good thing is, you go your left, you go right. You have a baseline or a back end of line, as you said it earlier, transistors, and then you have metals. So the physical effects all the way to, call it 90 nanometer, are very similar. So when we developed one deck, basically another 180 would look like a replacement of the parameters, but you don't have to change everything in the rules because the number of layers is similar, etc. So that's one example. In the We literally get it from the source of information. Sometimes this information is encoded into GDS. Like I give you a GDS, I say that GDS passes the DRC, and the other one fails the DRC, the design rule check. So now I have an AB kinda, and you use them after that for testing to see if the tool will catch the violation. So the foundry gives us this information under, because we to enable us to do it right.
And then the validation that you're doing then, so you're saying that that's happening in a tool like Magic, or what are some of the tools that you're using then to validate that you mentioned?
Talking about validating the correctness of the PDK itself or the design.
Yeah, that's right. So I mean, you said you're kind of skipping the PDK and you're validating yourself. So you must be doing this in some kind of tools. And like, how do you actually get to the point of like a source of truth? I guess.
Yeah. So the best approach that I call is that, generally speaking, to to start from the foundry and get from the foundry the way they sign off and test and stress test the rules in general. Basically, it becomes a bunch of layouts that have different variants of pass fail, and literally when you run it through the checker, you're expected to see 20 fails on these rules and 30 on this other combination of rules. If I don't see that, it means I'm not compatible with that. I mean, I missed something. So I use Magic to run on the same design. The DRC, or the manufacturing rules, the design rules manual, and the design rules themselves have to be the same. I can't just wave them. So we test against known outcome, which is we know a layout is violating, is by design, it's violating specific rules. So if I see that when I run my check locally on the open source, I know that I got these. Now, that doesn't mean that you have every single error under the sun is covered. And in this case, you start doing adding more layouts that have different structures, different components, different types of transistors, and you just crunch them into the checker machine, and then see what's clean is clean and what's not clean is not clean. And this process has a lot of good automation, so that
Yeah.
you can do it without actually having manual intervention.
So it sounds like it would be really tough to do this if you were working with, I guess you have known designs. I mean, are these designs that have been checked against processes for years and years and years? Is that kind of the idea? Or would it be really tough to do this as a leading edge kind of thing because you wouldn't have as many like validated designs that work?
So actually, for advanced node, let's say, back I worked on 20 nanometers in 2010. Back then it was really advanced, quote unquote. A team that develops pass fail layouts, and someone else is developing the checker. So they don't have the buffer. They have an independent type of blindness, so you don't check for what you know. So people do that until they figure it out, and sometimes they make mistakes and they end up with a bad silicon. Expensive, very expensive.
Yeah, yeah.
Yeah,
That'll ruin your Friday.
yeah, literally. I mean, if you
Yeah.
find a bunch of metals that are supposed to be parallel, they're all one slab. Okay,
Oof, yeah,
so
yeah.
that's one side. Now, the other side, which is going to be really cool, is because of the open source aspect of the Skywater PDK, you will find the number of layouts that are going to be generated. This is a public. So if we're actually building a place where you can store some of these store a manifest of these in a way that the collection of layouts that are available with known results are going to be available to people. So not just me can verify because I have access to sort of the menu through the
Right.
foundry. I
Yeah.
can have, anyone else can do that, and have tons of designs that they can use for the first time. By the way,
Yeah, and that will also allow people to make maybe some, calculated risks for, well, this hasn't been done before, but we ran all these other designs against stretching this one design rule, and now we feel we feel 85% confident that it's going to work based on all of these designs and simulations that we ran against it, and we're willing to try it on this process or something like that.
perfect. And there is a little, when you're trying new, there is a little bit of judgment. And I personally, when in doubt, I go check with the process guys. Why did you have this rule? Why? Is it because something optical, like if you don't have this rule done right, it's going to have a short circuit?
Mm-hmm.
Or do you want it? So I'll tell you, there's an amazing rule that it was about the width of the poly, and the aspect ratio of the given poly on a transistor in 45 nanometer, and on the transistor. So I was curious why. And he told me that when we do laser annealing, like annealing with a laser, so you heat it up.
Like a fusing kind of thing after the end of the line, or when?
Well, it's on the poly. There is a heating process that makes the chemicals, and the mechanical stresses just go settle in a certain way. It
Mm-hmm.
turned out that when you do it with laser, it gets in and the poly acts like a waveguide,
Huh.
and then it hits. If you have the length of the poly close to the wavelength,
Uh-huh.
it will actually become like a focused and it burns. It burned.
Wow, that's crazy. That's a rule that's been that came from experience. That's a hard one rule. It sounds like.
Yeah, so I'm not gonna discuss. I'm not gonna negotiate
Yeah.
that with him.
Right. Yeah.
So when in doubt, as I said, I go to the process. I ask why the rule is designed this way, and then because it's always sometimes they do it in a conservative way, like they tell
Hmm.
you, oh well, I can,
It's 40% greater than the last time they tried it, or something like that. Or
yeah.
yeah.
But keep in mind that there's one thing that if the process is stable, like something that's already been used for 10 years, you're very unlikely to have that happen because there's a lot of customers, a lot of users that are already used to certain rules, right? If you change the rule on them, then you immediately invalidates their whatever, depending on the rule, what the rule was, right? So in this case, you justify the effort. You see, okay, if the rule, if we change this rule, we're going to make the process more efficient. The tape out more efficient, for example.
Yeah. This is interesting to me because I used to always wonder, like, I talked to like TI, like factory application engineers who came through, and they'd be talking about, oh well, or we're moving to 180 nanometer, and this was like, I guess probably 10 plus years ago when I was talking to them, and like they were just getting to there as well. And I was like, what? I'm reading news stories about 45 nanometer or whatever is the newest thing. Why are you guys on 180? And they're like, well, it's qualified for analog now. And I never really got it. I always just kind of figured it was just like a trailing edge thing. But it really sounds like now it's like the fact that it's validating over and over again, especially when you want to tweak things a little bit at a time, right? If you're doing an analog design and you want to change the gate width by a small amount, or you want to do some kind of weird process step that is non-standard, you would want all these designs like you're talking about to validate it. And so it sounds like now having the open source stuff, it's just going to fast forward a lot of things, because it's not just, you can't, I'm guessing here, but I'm guessing in the past you couldn't have gotten access to a lot of designs outside your company to go and validate a design kit. You'd have to, sign a
Exactly.
bunch of waivers or something.
And if you didn't, if someone didn't experience that collaboration intensity and the quality of outcome that the open source community delivers, you won't understand, how this happens. It's crazy. You would think that you think it's unreliable, think it's not going to work. No, these guys are no politics, blunt. Okay, they
Hmm.
they figure out a problem, they tell you what it is, and sometimes they come with a solution as well. So having that is a great thing. Now you mentioned 180 is a trailing thing. Just any technology has a lifetime.
Sure.
You develop it and then you use it for many products and then you sunset it. So the 180 nanometer and 130, these things they didn't get sunsets. This is continued forever because first of all, one of the things if I try to iterate on some new architecture over and over again with the $10,000
Hmm.
versus $100,000 iteration, so it's cheaper to actually iterate, and that's a part of the Google picture here is that continuous integration, like the concept in the software. You put a chip, test it, and learn, and build another one in a lower
Uh,
cost.
also the Google idea of throwing money at things.
Yeah, that actually helps. So
Yeah, hey, we'll
exactly.
take it. Yeah, it's moving the industry forward. I'm good with it too.
Yeah, and when you start thinking about it, the last problem I have right now, like today, I want more designs. My problem is not finding money for the fabs. I'm actually the problem is in the design. The bottleneck is in the design. So we need more designs, and sometimes because of this, the fabs would voluntarily say, "Oh, I like it. I'm gonna just give you a shuttle."
Hmm,
Sometimes, okay.
interesting. And why is that? Because they want to also test their process for something, or what does that
Well,
mean?
once you have a design implemented on this process, it sticks, so it becomes a part of their portfolio offering.
Ah, okay, okay,
So, so they say, "I have this," and it's still owned by you,
right.
okay.
But they keep a
But
couple wafers. They get all the failure
yeah,
analysis data, and then they can,
yeah, and
yeah.
they say when a customer comes, if they comes, they say, "Oh, we have this data converter developed by this company or this person," and that's an enablement. So more IP and more functions means potentially more business.
Interesting. So what I'm hearing here is that all of the people that are listening at foundries right now should think about this because they get free IP that can be easily validated. Not that we have like a lot of listeners that are in the foundry business, but that is interesting as like a using the Skywater thing as a beachhead to try and get other foundries in the future and to be like, hey, look, you guys are missing out on all this IP over here. Why don't you go and offer this now in the future and also maybe open up your process and make it more of an open ecosystem?
And I think that's started to happen. I mean, if you notice that the main announcement that happened was Tim Ansel's presentation, and then the second presentation yesterday or 2 days ago. Now, and some Slack channel, but there is an announcement coming from official, like they're from the foundry, to say, okay, we're doing this, and then when you have this, that's going to be even more assertive to the market, saying a foundry has already come out and done this. Now, the benefits, what's the rationale for the foundry to do this? Not just the validation of IP or availability of IP. Here's the thing, statistically speaking, if you increase the number of designs, the chances of one of them to hit the jackpot in terms of market increases. If you only do two, you really, really have to be careful to try to make one of them or two of them really hit the market and make revenue. But when you have, 100 or 1,000, so the philosophy is very simple. I'm going to enable as many people as possible with open source tools and process, and then that increases the statistics of someone coming to me with the foundry. This is the foundry hat, coming to
Right.
me with a design that needs to be a product.
Yeah. Yeah, because at the end of the day, they just want to make as many chips as possible, and so yeah, it is. It's basically just another. I mean, it's a marketing tool at a certain point, right? But it's also there's benefits on the other side. So yeah.
I call it a currency. So it's
Uh huh.
almost like in order to build an IP or a block in a given technology, you're basically converting your money into that currency.
Like itchy and scratchy bucks in The
Yeah,
Simpsons.
yeah, yeah. And that currency has to be, if it's not used, then you lost your money. You just
Yeah.
bought you
Right.
bought a wrong currency. Okay,
That's right. Yep.
so the foundries need to typically be in the process, although they don't say it, but they they say it in a way that my currency is good and it's fluid and people
Mm,
can use it and make
right.
chips with.
Right.
Now, when you see that, people will come in and say like, "Oh, I'm going to convert my money there, or my time
Right.
rather."
Yep. Right. And so you're saying in the past it was fiat currency, and now it's a Bitcoin style.
Yes, yeah. In a sense,
More fluid.
the one last thing that happens here is that the foundry. So it's interesting that there's a process that people always, okay, when the foundry comes up with a new thing, the first customers become the guinea pigs. Okay, they try and then over time, the foundry, when they sell to more customers, the quality of the output of the PDK, for example, increases because of the
Yeah.
several loops of trials and
Yeah.
errors.
Yeah. Yep.
That's a serial process to a certain extent. If it's a new thing, when you do it with the open source community, I mean, I saw an example for the Skywater, even though it's an already established process. We have in a couple of days 200 people join the Slack channel, at least 10 of them saying, I'm here, I want to help test it.
Was this about 2 weeks ago? Because I mean, I'm going to take credit then.
Well, yeah, yeah,
If it
you
was two
could.
weeks ago, then it was the amp hour. If it was before that, well, okay, then that was. I'm sure that was. Yeah, it was the announcement. That's really
And,
great. Yeah. So you're saying that basically enables just more parallel processing. Basically,
and
you're.
that is amazing because statistics, and when you have parallel tracks, three paths to do the same problem, if each path has an 80% of hitting the problem, and you do three, it's 99 something percent.
Yeah.
So,
Yeah.
and then people, they sometimes if they make a mistake, oh no, I found it, I made it work, and this way, and they say their solution, and then the solutions become a documentation.
Hmm.
It's a fascinating world. It, I do think that, however, in order to post Google world, meaning when I say post Google, meaning in order for the semiconductor industry to change, you can't have just Google paying money to make
Yeah.
free shuttles, right?
Right. Right.
So there needs to be a change in the dynamics, which we believe we've been focused on it. As crazy as people say it, we've been focused on it to reduce the upfront cost to get to a prototype and prove the design or prove your idea.
Yeah.
From then, you can choose to go back up or down. And in this case, you have much more leverage. You have much more value in the idea, and versus I have this idea that I will do if you give me the tools and the process and.
Yeah.
So one thing that I didn't mention here, we've been talking about people who make chips, okay, design chips, who know how to design chips and play with chips. Well, one of the objectives that we have, I mean, it's not rocket science, okay? So it's kind of a shame, basically, to have the process of creating a chip since its inception. It hasn't changed.
Well, it's got a little smaller, but yeah, it's still p area, n area, or
Yeah,
equivalent, and MOS process. Yeah.
but the intent, well, it changed obviously in the steps, and there are details. However, there is designs, there is modeling, there is create the front end, back end, and creating GDS, putting your foundry. Well,
Mm-hmm.
the one thing is that when you listen to this process, it requires a lot of knowledge.
Mm.
Well, I think, and that's what we're doing in Harvest, is that we need to simplify it to the level where I don't need to know how it's made. I just want to use it, and I tell you what to do. So if I were building a board, and if you go to the Fabless website right now, just on the landing, and it's going to sound like marketing, but it is, in a sense, it's a good thing. So I'm going to say it. If you go to the main website, you're going to find a template in front of you. It's called Raptor.
Yep.
And when you click on Raptor, this is an ARM-based chip that already exists, and I have a board for it. And if you click more, it asks you, tell me what peripherals you want in a point and click.
Yeah.
And you add. So this is an interface. Who's using that interface? Not the chip designer. Is a system designer who says, I just need that much RAM. It's like a selector guide. I need that much RAM. I need 2 ADCs. I need that.
Right. This is basically it's a part family. It's like looking at a part family that has 80. I don't know how many variations there are, but basically it's every variation instead of like having to look at the table from like a microcontroller family, like an STM32, and saying, well, there's all these different options, but you only get like 8 total options, or maybe 64 total options of
Yep.
all the combinations you have there. There's as many options as the combination can have with this.
Yeah, and the more people add, so for example, someone comes up with an accelerator, you can add it there on their ownership. So now, if the system developer uses that accelerator, that validates it, and there is actually a business relationship that actually, even if it's open source, the fact that accelerator is used as a and served supported by the developer, it's a value for the receiver. But the language here this is abstraction, meaning that I don't need to know. I don't want to hear GDS. I just want to tell you what I want in the chip, and you.
Right. This is a menu ordering system, basically. This is
Exactly.
yeah.
And the numbers for it you'll find on the mains website. If you stick to that template, and we call it a template, and the list of options in the menu, you're guaranteed to get your product in chips in $70K. $70K. This is a company that's building, not this is someone who's receiving the chip, not developing the chip. Okay, developing the chip is much less because they apply their own experience. Receiving the chip, this number is probably at least 5x.
5x less, you mean, or 5x more?
Less.
Sorry. Okay.
Yeah, less.
Okay,
So
that's
when
good.
you say it's $70,000 to get the first 100 parts of my product, this is a very low entry barrier, and that's for the recipient, as I said, for the recipient, on the other side. And typically, when you go, it becomes start at a $200, $300,000 to. Now, why is that number low? It's not because the chip is smaller, or maybe it is smaller, but because it's template, so it's pre-engineered. So some of the engineering time that you already spent, it's already in it, and the changes that you're making are restricted to controlled changes. Like you put them on the bus, like the old computers where you slide the card into the back of the computer.
That's right. Yeah, ISA slots and stuff.
Exactly that.
Yeah.
Exactly that. So have a bus and
Hmm.
just hook up the things to it, and then the more you add, you just calculate the area, calculate power, da da da, and then so if you're doing that, you're guaranteed that the motherboard, you can fix the motherboard. You don't have to verify the motherboard every time. You have to
Hmm.
verify software, but not the motherboard.
Mm.
So that's the
Yeah.
equivalent.
Okay, so I hope you don't think I was listening, but I was clicking around as I was doing that. And in the amount of time from when you started talking about that to now, I just designed a chip. So like if people want to know, I was pretty much clicking, I saw a click and I just did a click, but like that's about how long it takes. So that was about a 4 minute process to make a complete, not a completely custom, but like I just configured a chip. That is really cool. I mean,
And you
like
can save it, and
yeah.
if you notice, you're going to find the cost,
Yeah. So
and
it's $1.62
yeah,
part cost.
yeah,
Die
and
area is
some
5.35 millimeters. Total IO is 44, and then licensing cost $0.
yeah, because the IPs are on that chip specifically, they're not they're presented as a part of the package. It's not presented.
Uh huh.
Now someone can put you know can put their IP and say, okay, it's going to be X cents per part, whatever,
Hmm.
and that shows up in the calculation. And so that gives you information about decision. You can actually save multiple configurations. You can configure it A, B, and C,
Yeah.
and D, and then now you'd have multiple options with different costs, different trade-offs.
Hmm.
So it's a very powerful tool. And then now, just to complete the dream, once you do that, there are two ways of getting the chip finished. You either someone of experienced in making chips that will take your RTL, because by the way, whatever you did on the form, it goes to become an RTL.
Hmm.
So it's not, it gets compiled into a code, Verilog code that is ready to go to backend to be hardened to the layout. Now we're doing that with OpenLane.
Okay. So that it's now configurable on your computer instead of with a
Yeah, and
clicking thing.
by the end of the clicks you had, you can literally click and wait for the right number of minutes or hours depending on what the size of the chip is. And like Strive would take a couple hours.
Okay.
Okay.
Yep. And when you say a couple hours, is it like so? There's like a flow, and like so we will link to the actual open lane. So there's a GitHub page for it and all that. But is it basically just like a make command? I mean, what is it to actually kick off the
So
process?
if you're using the flow on our platform for a system, there are people who just want to get the chip. You don't want to deal with the flow, right?
Uh
In
huh.
this case, the last step of your form where you said click and here's my configuration,
Hmm.
it gets passed automatically to farm that takes it, passes through it equivalent to the make file, a sequence of steps. Each one of them has an outcome, and then it runs all of them, and it gives at the end of the last one is the GDS. But
Wow.
that starts from synthesis, and then you store that synthesis output so that you can verify it. And then
Huh.
you go placement, routing, DFT, etc., and you can store that. Now it gets stored, but if I am the person who doesn't care about, I just want the chip, I don't care about that. It's hidden inside the cloud. Now, if I am doing it the open source way, when you clone the open lane, it's a make. So or basically it's a, you can do multiple layers. I mean,
Yeah.
we did it
Right.
in a Docker container, so to make it easy, and then the another way to do it completely native. But basically, it's a sick. You put the chip, you give me the design, you give me control files, and then run and leave it.
Huh.
And
And
then,
then
by the way,
so
this is an
yeah.
important part of
Uh-huh.
OpenLane. I'm sorry to is that now it's what if it didn't finish? You know,
Hmm.
so I like Tim Ansel's expression, and I give him that coined it. I don't one design rule violation is like 1,000. I don't know what to do with it.
Yeah.
So the goal with OpenLane is to get you completely clean, ready to go.
Yeah.
Well, you have to, in order to do that, the first configuration you put in terms of backend, how they're floor planned, how their the hierarchy is managed, etc. It may not get you that first round. So you change the configuration. Well, that you keep doing that. Well, you could do that manually, but the flow had a picture like this. It says try configure. We have a set of configurations A, B, C, D, and then try them one by one and see which one gets you to the zero tier, ready to go.
Hmm. Yep.
And And then now, just to calibrate people, because it's the way it's done, I'm not going to say I'm benchmarking it against any other commercial tool. I say it's the best benchmark because this is the only open source way to do it. That's one.
Hmm.
So
Yep. Yep.
there's no other.
Take what you get.
The
Yep.
Yeah, what you get. The second one is that you sacrifice area, you sacrifice other things, but you don't have to be knowledgeable of chips to get it.
Yeah.
So that's the key part.
Right. And it's interesting too because I mean, I think one thing I think about with this is the idea of like adding adding exactly what you need, or maybe it's a you just couldn't get the exact part you needed with an off the shelf part. Now you actually have an option. It's
Yeah, and I have a
essentially
friend of
different.
mine that calls this the right size compute or right size
Hmm.
thing for what I want to do,
Right.
rather than getting stuck with the standard. And of course, there are standard parts that are really fitting what you're doing.
Hmm.
Yeah, but you know, deviation is deviation.
Yeah.
Especially when you come to form factor, power, memory, things like that.
Yeah. I mean, like as the practical example, I mean, like it would be really hard. It would be really hard to buy a off-the-shelf microcontroller that had 16 UARTs, but it does seem like it's possible here. Is
Absolutely,
that correct?
yes.
Okay, that's pretty crazy.
And we adapt. Like, for example, in order to put peripherals on the bus needs to adapt in terms of loading and other things. This is all in
Hmm.
happening in the background.
Yeah.
Yeah, so exactly that, as you said, because no one is going to tell you why, if
Right.
that's what you want, if that's what you want to do.
Yeah. Right. Yeah, and it's you're not like talking to every vendor and asking like, well, do you have 16 UARTs? And they're like, no, why would we have that? We need to sell to more than one person. We need to sell, we have to try and like hit it's like the Venn diagram. You have to try and hit as many people as you can. And just that one dot that's outside the Venn diagram, you're not going to make a custom chip for that person. But sometimes the weirdo needs 16 UARTs.
Yeah, yeah, and I ordered ADCs or amplifiers or
Yeah,
something. I
right.
mean,
Yeah.
and you could prototype it some other way, and that's what happened with one of our customers. Actually, they did a board to prototype the whole thing, and
Hmm.
then he said, well, half of that board needs to go on a chip.
So I mean, how can people get started? What does it take to actually get to that point? Is it mostly just click like I did and register and then
So there are two places. If you're passionate about developing and understanding how it works, you go to openlane.io.
okay.
It'll take you to the right place in terms of GitHub, and it has instructions of basically like systematic instructions or executable make,
Hmm.
where you clone and run it on your platform, and it comes with about 40 examples inside it. So
Wow.
you can run any one of them. The process has inside the open lane instructions how to bring in the Google PDK in as well, because you
Okay.
choose which library. All of that is included there. And then you if you have an RTL code Verilog, you can certainly use it and get your GDS right there.
Huh.
That's it. If you want to get your hands in the down there and basically dirty with the flow and getting in the plumbing. If you want a chip and I don't care to run no open lane. I don't want to hear about open lane. All I want is this chip that has 16 UARTs. Okay.
Someone listening right now, they're like, "Oh my god, I have been waiting."
Yeah, and of course, there's that like the company that I mentioned is Have the Chip. They actually calculated it and found that the ASIC will actually make them make more money in terms of margin for
Yeah,
that product, for their
that's
product.
great. Yeah. There's no better way to like prove to your boss that you need to be doing something like this than to be like, oh, hey, money, look at the dollars, dollar sign, dollar bills, y'all. Like
And I think that's the reality we live in. So as much as open source is a great thing,
Hmm.
in the hardware world versus software, because of the cost of materials and the actual failure, if you fail, if you don't, if iteration, the cost of iterations, because failure is okay, you can reiterate, right? But
Hmm.
because of that cost, it creates, where do I get this money? Because
Hmm.
it's actually physical stuff, real hardware, real things in your hand. So it's important to have a business model to continue to draw and keep that alive. It doesn't mean you sell your open source product. It becomes maybe something like maybe in some areas becomes like, the closest example is I developed an app or a stack, or so quote unquote design, and then a customer comes and says, I need that design, you customize it for me.
Yep. Yep.
And then now, because you as an engineer or developer, the earning there becomes, I made my design work for your system,
Yep.
but the design is open source, and the
Yep.
customer doesn't know how
Exactly.
to deal with it.
Yep. Yeah. They basically, the open source was the marketing that allowed them to see it and see that you have the capabilities to make this thing happen. Actually, we had Ryan Cousins, who was on the show. He talked about that with the board Snickerdoodle that they made. It's like this FPGA development board. He said the
Mhm.
main part of their business is not selling the board; it's selling the customization for that board, because people find out about it and then they say, "Well, I don't want to deal with it. You do it." And then it's basically the exact same thing.
Well said. This is exactly what it is.
Yeah.
And we had away from it being, just as a reality, when we were published
Hmm.
Raven on GitHub,
Hmm.
we got contacted by NEC research
Oh
group,
wow. Yeah.
and he said Raven is good, we can do certain things with it, give us some boards. We gave them some boards. However, very quickly came back and said, well, I need that much memory, I need NVRAM, I need this, and we created Ravenna. So you'll find a chip called Ravenna on the platform. That's
Uh-huh.
a customized version of Raven based
Yeah.
on a customer input.
That's great. That's great. And then that comes back, and that's another design that can be
Another
used
design,
again. And yeah, right.
and we have it with
Interesting.
the board and everything ready to go.
Yeah.
So people can, we send these boards to the customer so they can actually develop and write, test it for their own prototype at the system level.
That's super cool. Well, Mohammed, this has been really great insight into this. Where can people find out more about you specifically, but then also the company?
So Twitter, MK Kassem, LinkedIn, MK Kassem. The company, I'm on the website of the company, and I'm for sure that I'm inside the Slack channel, or the Slack space for the OpenPDK, and
Great.
and I want to share with people is that we're going to create a sign up form that is a sign up self invite. So I don't have any
Mm-hmm.
people don't. You just go there to that place. It's going to be
Mm-hmm.
called join.skywater.tools.
Join this guy.
Join.skywater.tools. It's not ready yet, but it will be
Okay.
that.
Okay.
People will sign up to the Slack channel space, and they just get into that.
Right. Instead of having to ask for an invite or use the invite link that, yeah. I'm not sure why Slack did that. It's like one of their, yeah. Anyways, Slack is its own thing.
Well, whether you hit or like it, it is right now. It is the actual right now. Would benefit. I mean, the group of people. We have 300 people right
Yeah.
now in that space.
Mm-hmm.
They're collaborating in multiple rooms,
Yeah.
analog, digital. This, and it's working. But GitHub
Yeah.
is always in the back end, because if something has a bug, somebody has a bug or an issue or an improvement, they file it as a GitHub. So GitHub
Issue.
is
Yeah.
is also, but that's and about the company, you go to efabless.com and register. It takes you 10 minutes. You don't need an NDA or to pay to access any of these resources to design your own.
Right. You don't even need skill like I just showed. I mean, I just clicked and I made a chip. So I'm going to go put chip designer on my resume now. So thank you for that.
Well, and that's actually how it should be, to be honest, because driving the car isn't, you don't need to know how the car works to be able to drive it.
That's a good analogy. Yeah.
So,
Yeah. Well, thank you for joining us today. I really appreciate it. And I'm looking forward to chatting again in the future.
well, thank you for having me. Appreciate it.